Hey everyone, welcome back, and today let's solve Leetcode problem 1123 titled Lowest Common Ancestor of Deepest Leaves. So we're given the root of a binary tree and we want to simply return the lowest common ancestor of its deepest leaves. Now we need to also recall that the node of a binary tree is considered to be a leaf node if and only if it has no children, or no child nodes, meaning no left and right subtrees or subnodes. Now the depth of the root of the tree is always going to be 0, and if the depth of the node is considered d, then the depth of each of its children would be 1 greater than that depth to be d plus 1, because of course they're in one level down. Now, the lowest common ancestor of a set S of nodes is the node A, and that node A is going to have the largest depth, such that every node in the S set of nodes is in the subtree with that root A. So in example 1, we have our input binary tree. Of course, we're given just the root of the binary tree, but to kind of give us an image to visualize it, the root node would be 3, and our nodes with no children would technically be 6, 7, 4, 0, 8. But we want the deepest leaves, and we know that's going to be on depth 4 or level 4, which are the 7 and 4 nodes, right? Now we have an output of 2, 7, and 4. Why? Because that's going to be the lowest common ancestor of these two nodes, 7 and 4. Why do we want the lowest common ancestor of 7 and 4? Well, because those are our two deepest leaf nodes in the binary tree, right? That's why we have an output of 7 and 4. Now, going back, we see that nodes 6, 0, and 8, they're still leaf nodes. Why are they still leaf nodes? Well, because they still have no children, no left or right subtree nodes. However, if you go back and look at what the definition of the depth is, we know this has a depth of 0. We know these two nodes have a depth of 1. These four nodes have a depth of 2. However, these two nodes, 7 and 4, have a depth of 3. We want the leaf nodes with the deepest leaves, otherwise also known as the leaves with the deepest depths, and those are going to be the nodes 7 and 4, hence the reason why we only find the lowest common ancestor of 7 and 4, which we know is going to be in the left subtree that connects them, which is going to be that 2 node, right? That's the reason why that's our output for those two corresponding 7 and 4 leaf nodes. In example 2, we have the input root binary tree to just be 1. We only have one level, you could say, call it the 0th level if you will, and that is the singular root node itself. So that's also going to be the deepest node. It's also going to be the LCA of itself, because any node is technically the lowest common ancestor of itself. So yeah, I mean, that's really just a straightforward output. And finally, in example 3, we have our input binary tree to be 0, 1, 3, null 2. They don't give us an example here, but just quickly, we have an output of 2, because that's the lowest common ancestor of, well, technically itself. Why? Because the deepest leaf node in the tree is also that node 2. If we kind of plan it, or kind of depict it out in a picture, and so that would be the deepest leaf node. Of course, 2 is going to be the LCA of only one node. It's going to be itself, and so we just have an output of that 2 node. So for the constraints here, we see that the number of nodes in the tree are always going to be in the range from 1 to 1000. Any value in the node, or any value of any node in the tree, is always also going to be between 0 and 1000, and the values of the nodes in the tree are all going to be unique, kind of just confirming what the problem statement said, and telling us that, okay, we don't have too large of input constraints. Maybe something even like, recursion or a DFS would work here, which actually is exactly how we solve this problem, right? Because we don't have too large of input constraints. So let's go ahead and kind of see some main observations to make in this problem, and how we can really solve this for the context of this problem, relatively, at least in the most efficient way as possible. And again, what is that main observation that we can really make? Well, really, it's that all the deepest leaves, they're all going to be, if they actually do all belong to that same subtree, well, then we know the answer, or the lowest common ancestor, is basically just the root of that subtree. But what if we have in a different case? What if the deepest leaves in our binary tree, what if they're spread across multiple different subtrees on their depth level? Well, then we need to find the lowest node in the tree that connects all of those nodes, kind of minimizing its kind of depth as much as possible, right? To kind of get the lowest common ancestor, right? Not the highest, not any ancestor, the lowest common ancestor. So how are we going to solve this problem? Well, I kind of just glossed over it a few seconds ago. It's going to be a depth first search or DFS approach, also combined with recursion to go through all the possible left and right subtrees or nodes, subchild nodes for each node recursively. And effectively the way that's going to work, we're going to actually traverse the tree again using that DFS or depth first search kind of operations on the tree, and at each node we're going to compute the depth of its left and right subtrees recursively. Now, to actually compare those depths to find our lowest common ancestor, we know if the left and right subtrees have the same depth, then the current node that we're currently visiting, it has to have it's going to be the lowest common ancestor of the deepest leaves in the binary tree. However, if we know one subtree is deeper, whether it be the left subtree or even the right subtree, well, then we know that the LCA has to be in that whatever deeper subtree is, and so we have to return that deeper subtree's result for that call of the function or method, and recursively go on and explore the more child nodes from that LCA or position. Right, and effectively, once we fully complete our recursion, we're going to return the LCA of the deepest leaves once we actually fully kind of compute the function and all of its calls across all the nodes in the tree. So let's go ahead and get into the code here. So I'm just going to really just directly define my DFS function here. I'm going to call it DFS in this case. Usually I call it backtracking, but this isn't necessarily backtracking. It's really recursion and more of a DFS type approach rather than backtracking. And for my parameters or input parameters for my method here, I'm going to take in one parameter. It's going to be the node that we're currently visiting. Right, it's going to be the node that we're currently kind of trying to find the left and right depth, child tree depths for. Right, and again, what is this entire DFS kind of method trying to do? We're basically just using it to calculate the depth of each left and right child nodes or subtree of each node and finding that lowest common ancestor of our deepest leaf nodes. Now, in DFS and recursion methods in general, we always have our base case first. In this case, our base case is, I would say, rather simple. If the node is non-null, in Python, that would mean if not node, meaning it's kind of false, well, then we want to return a tuple of length 2. You first want to return its depth, its depth is going to be 0, and we then also want to return none. None is basically, well, that node itself, because we're confirming, if we're in this conditional, that the node is non-valid, or in other words, it's null. If it's null, well, then we want to return a depth of 0 and none, kind of indicating that it's null. That means we reached a leaf node's child, we have to return 0, none. Why? Again, because that's indicating that we have a depth of 0 and we don't have any LCA for that node, right? Because we've literally reached a leaf node's child, which a leaf node is defined not to have any children, so this is literally an undefined node, if you will. Now, once we actually complete our base case, we then actually want to move on to the recursive calls and methods of this function, right? That's going to be the recursive call DFS for the left and right subtrees of the current node that we're at, right? So we'll get the left depth, because of course we're returning two things here in the method. We're going to return the depth of the subtree and the actual node or root of the subtree itself. So we'll get left, I'll call it left depth actually, and we'll get left LCA. Again, keep in mind LCA stands for nothing but lowest common ancestor, and it's going to be that recursive call on the left, you guessed it, our subtree or node of our current node. And very similarly, we'll get the right depth and right LCA. Sorry, I forgot my depth. And you guessed it, is going to be the recursive DFS call rather than the left child or left subtree, the right subtree of our current node. Right here, very, very straightforwardly, we're recursively calling this DFS method on the left and right children of our current node, where we're basically computing the depth of both of those subtrees and returning their LCAs if we find them, if they're actually valid nodes in the binary tree. Now here's where that kind of deeper LCA logic kind of comes into play. We have to actually compare which subtree is deeper, the left subtree or the right subtree with their depths and root nodes, if you will. So if the left depth that we just calculated in the previous recursive call, if it's greater than the right depth, well, then obviously the left subtree is deeper than the right subtree. If that's the case, we want to return that left depth. But keep in mind, it's not going to be the left depth itself. It's going to be left depth plus 1. And we're also going to return the left LCA, which is all stored or calculated on lines 12, because in every single call of this method here, we're returning two things. We're returning first the depth of our current subtree, and we're also returning the node itself, or rather the root node itself for that subtree, right? Now, what if the left depth isn't greater than the right depth? What if rather the right subtree is deeper. If that's the case, we can predict that very straightforwardly. If left depth is less than the right depth, that means again the right depth or right subtree is deeper. Well, then we know that the LCA has to be in the right subtree, and so we want to return the right subtree's depth along with its root node, which is going to be right depth plus 1 to account for that height with the LCA and child node, and then right LCA. So here, this is saying if the right subtree is deeper, we know that the LCA has to be in the right subtree. However, if the left subtree is deeper, then we know we have to be, the LCA has to be in the left subtree, because we know the deepest nodes, i.e. the left nodes, are always going to be in the deepest most subtree, because that's exactly how they're defined to be. And finally, we'll have an else conditional here, and look like I just forgot, there should be elif, not if. We want to keep it in the same kind of condition block, if you will. And finally, an else conditional if neither one of these conditions are true, meaning the left depth is not greater than the right depth, and the right depth is not greater than the left depth either. Well, then, kind of by logic or by process of elimination, we mean, if we're in this else conditional, it means that both the left and right subtrees have the same depth. If that's the case, we really can do whatever we want. I'll just return the left depth plus 1, but keep in mind the left depth and right depth would have the exact same depth if we're in this conditional, because that means it's equal. We haven't entered these two conditionals where one of them is greater than the other. And of course, along with the depth, we're also going to return the node itself. That means that both left and right subtrees have the same depth. The node would be the LCA of the leaves. When I say the node, I mean like this specific node that we're currently visiting, the node parameter in this call of the method. That means this specific node is going to be the LCA of the deepest leaves if the left and right subtrees have the same length, or depth rather. And so we simply would just return one of them, one of their depths plus 1. Node doesn't really matter, and then the node itself doesn't really matter which subtree left or right, because they're the exact same depth. And now that we're kind of done with the definition of this DFS function, now we want to actually return our answer. So we're going to return the DFS call starting from the root node. Now we don't want to return the tuple of length 2, obviously, right? We don't actually care about the depth in this problem. We only care about the lowest common ancestor node, and so that's going to be the actual node that we finally return for the deepest leaves in the answer. So it's going to be, instead of just the DFS at root at 1. We're basically getting the answer of DFS at root, the final answer, i.e. the lowest common ancestor of the deepest leaves, and returning index 1 of that tuple of length 2, which would basically be the node that we're returning. It would basically be the LCA of that final call, right? So unless I made any syntax errors here, this should be accepted, and there should be a final accepted solution. So let's go ahead and double check that. And as you can see, this really is just about as efficient as you can get it to be. Kind of funny how it says exactly 1 millisecond. Anyways, so on a high level, what are we kind of doing here? Just to kind of quickly reiterate, basically, we're actually defining our DFS recursive function to actually traverse the entire tree, and we're then computing the depth of each left and right subtree for each node that we kind of process or iterate over in each method or call of the function. And we're actually recursively finding that LCA by comparing the depth of the left and right subtree for whichever one is greater. But if the depths are equal, then of course we know that the current node itself is going to be the LCA. Otherwise, we simply return the LCA from the deeper subtree, and this final call, DFS at root, is going to be the lowest common ancestor of the deepest leaves starting from a recursion from the root node, and we're returning that answer at index 1 because we only want to return the node itself, i.e. the LCA. We don't want to return its depth, right? That's going to give us the LCA of the deepest leaves. So for the runtime complexity here, quite straightforward. It's really just linear, i.e. big O of n. Why? Because this is really a straightforward DFS approach where we visit each node exactly once in the entire binary tree. And so big O of n is simply going to be n being the number of nodes, and also going to be the runtime complexity. For the memory or space complexity, it's not really constant. Why? Because recursion does actually take up space. There is something called recursion stack depth, and that in this case is going to be at most big O of, I don't know, h, and h is simply going to be the height of our tree. Why? Because in the worst case, meaning we have this kind of skewed tree, well then h would be n, right? Because of course we have one node in each level, meaning h is equal to n, and so that would make our space or memory complexity big O of n. However, in a balanced tree, h would technically be log of n, and so that would kind of make our memory complexity big O of log n, but really you can think of it as big O of h, where h is really just the height of the tree on average. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.